他两点都在对比，点多还看到这事情。
已解锁，请取出话筒。
Wait for another moment. Exactly.
还在冲凉，
Okay, then let's not wait for him. Okay, last time you guys are pretty confused like what you did, right? What not to write in assignment, right? So I think one very important difference between mathematics or just calculation is you need to know what you can assume and what you can use. Okay, this is the difference. Because if you just plainly look at this calculation, right, you will see that I just simply bring limit in. Things possible. Okay, seem possible, and then seems like answer work out. But why can we do that? and then this should be answered by mathematics. Okay, why we can bring it in? You know why we can bring it in? Property of convergent sequence. Okay, it's because we know that inside that quotient we have convergent sequence, so that we can do that. Okay, it's not that we just try, work out, then work out. It's not like that. Okay, it's not just by calculation, it's you already see convergent sequence inside there. Then you can bring the limit in. Okay, if you don't see it, you cannot just bring it. Okay, maybe you can do some working, but you cannot write it out as your solution. Okay, if you don't know that 1 over n is convergent. Does it make sense? Okay, no. So this is the difference here. That's why every time I will say that when you write some equality sign here, you must tell me why is it true. Okay, you must tell me that why is it true. Okay. And then we know that 1 over n converges. Okay. So calculation wise is okay. Okay, calculation wise is okay. But why you can use that calculation is very important. Because in future you will see very exotic example. Exotic example meaning you think that you can bring limit in, actually you cannot. Okay. Does it make sense? Because if you do those high school maths because they already set the question such that you can always use it. So you don't need to ask question whether you can use them. They just want to test you whether you know how to use them. It's not you know why. Focus on more how. Okay, it's not why. But in the university level, we will focus more on why. So we will give you more exotic example to tell you that it actually sometimes doesn't work. Then you will know, oh, actually I need this to be true first, so that we can use the calculation. Does it make sense? So that's why we always ask you to put down reason why. Because you will meet a cases that it doesn't work. Then you will make a problem that case. So this is why we focus on explaining why. Okay. Yeah. Right. One thing, right? Humble is not here. Humble not here. So Jianpeng, you was right something that you didn't prove in your assignment, right? About this ln 1 plus x greater than x or less than x. Actually, Humble did in his assignment. You can try and check with Humble. You know Humble? Yeah, you can ask him. Actually, he write out that proof. Yeah, and then I give him credit also. Ask him. Okay. Right. So we try to finish series today, and then we go into a little bit of Fourier series. Okay. And then I think, are you guys okay with submitting assignment tomorrow or not? Not tonight. Huh? Of course. Others, eh? Okay. Okay, good. So in that case, I will release assignment 3 maybe tonight or tomorrow. Huh? Why? No, you can look at it on Monday, but I will release it. Okay. But maybe give you some mental preparation. I don't want to shock you again. So mental preparation of this assignment 3 was there will be a question on proving, but for that question, it will be guided step by step. So you'll see very long question because it was guided step by step. So in each step, you should figure out why is it true. That's the only thing you need to do. Okay. The content of the proof is already provided for you. Just that you need to explain why each step is true. Okay, and then that proof is about proving pi is irrational. And prove that square root 2 is irrational. Right? So that question is about pi is irrational. And then we will use Fourier series related idea of periodic function. Does that make sense? Actually, that question is extracted from Adam. If you like, you can go and find in the textbook. But in that question, right, although I guide you step by step in the proof, but I want you to organize your answer into a proper proof. So meaning you need to write some like essay or proof essay like that. Maybe it doesn't make sense now. You will see it when it will make sense when you see it. Don't cry, don't cry. Don't cry. But yeah, try to learn to write proof. Okay, yeah. Try to learn to write proof and then try to learn to read proof. So we try to do within your ability what you can learn now. And then in future it will prepare you going to more abstract proof. Those proof are abstract. Okay. Now you still can see a proper function and number or what. But in future those proof will be abstract. Okay, abstract meaning you see very few examples inside the proof, but what you will use in the proof is just some definition, properties, abstract definition. Okay. Does it make sense? Okay, so try and learn more proof writing this class. Okay. Good question. Okay. Yeah. Then I think only that question is pretty long, and the other I think is computational. Half proof, half computational. And then others I think pretty short. I wouldn't say straightforward. You should think a little bit about those questions, but the solution is short. We can discuss again when I release. So you should think about it when I release the question. So usually when I release the question, right, I like you to think about it first. Yeah, I would like you to think about it first. Okay, don't be nervous or what. Think about it first. You don't need to straight away do one. You can look at it, don't know how to do, put it at the back first. Put it at the back in your mind, and then think about it, and then come back again. Cannot finish, put there again. Go do other thing first, and then come back again. Keep coming back. Okay. I don't expect you to just sit there and then finish it. It's not like that. Okay, that one is homework question. Okay, you can do that for your homework question. But this one is assignment. Okay or not? Okay. So don't be how to say depressed if you don't know how to do. It's normal one. If you know how to do, you don't need to sit here already. Fair enough. Yeah. So you should think about it over and over. Okay. So we'll start new content now. So we will introduce term by term differentiation or integration on power series. Okay, so what does it mean by term differentiation and integration here? So similarly we'll start with a power series. Okay, so what's the power series? We have a coefficient time monomials, and then we take all the sum of integer power. So this power series here, if it converge, right? How does it converge? It converges. There's three kind of convergence. Three kind of region of convergence, right? Either it converge at one point, either it converge within an interval, either it converge in a real line. Only three types. Okay, only three types. So how we characterize these three types? We characterize by the radius. Okay, we characterize with the radius. Why we can always talk about radius? Notice that the interval of convergence is always symmetric. Okay, symmetric about where? Symmetry about where? Symmetry about where? Or do you still remember any example of interval of convergence? How do you write down the three kind? 建同 You didn't pay attention, so who pay attention does not? Tell her then? No. Yi Xiang? Ah, no. How about Chuan Yu? Chen Yu. No. Do you understand my question or not? Huh? So do you know how to write down the three type of interval convergence for a power series? What are the three types? I think just now, Boon Ping talked about three types, right? So what are the three types? What are the three types? And then, okay, cool. So the 1 point is where? If you talk about minus r plus a to a plus r. A. So where's the center? A? Or L? True or not? Is it A? Is it A or not? So when we talk about minus r plus r to r plus a, where's the center? You know how to compute the center or not? How? How to compute? You find what? Midpoint? How to find midpoint? High school question. How to find midpoint? Along a straight line. You add the endpoint and then divide by 2. You get A or not? So you get the midpoint to be A. Okay, so it's always symmetric about A. So what's special about this A? When you get this A, so you should look at your power series there. Okay, so what's your factor for your X? Okay, if it's just X, then your A is 0. So you can shift your power series. Okay, you can shift your power series. So if you have a power series that's centered at A, have radius of convergence, okay, then what? Then this theorem tells you that the function defined by this power series here, if it converge, then this function will be differentiable on the interval a minus r to a plus r. Okay, and how do you differentiate it? Okay, so every term inside this series is what? It's just polynomial. Polynomial, you can always differentiate. Is it true? You differentiate x squared, x cubed, x to the power 4, x to the power 5. You can always differentiate, right? So how do you differentiate it? You just differentiate term by term. So you can think of it like a linear operator. But this is linear for infinite terms here. Okay, so you can do it infinitely many terms. Okay, so how do you differentiate the first term? So the first term you'll get what? What's the first term in your series? N equals to 0. C0 is a constant. So if you differentiate it, what do you get? 0. Okay, so C0 will disappear. What's the next term? C1x. Okay, if you differentiate C1x, what do you get? With respect to x. C1. Okay, so you're left with C1 2 times C2 times x minus a. And then, can you predict the next one? Yeah, 3c3 x minus a, power reduced by 1, so you get squared, and then so on. Okay. And then second thing is you also can integrate it. Okay, you can integrate it from your center. Okay, from center to some x inside your within your interval of convergence here. So how do you integrate it? You just integrate term by term as well. So what do you get? So first term you get c0 times x minus a, and then half time c1 times x minus a squared, and then so on. Okay. So after you differentiate, after you integrate, it's still a power series. So you can ask again, what's the radius of convergence? Okay, when you look at power series, you can ask about radius of convergence. So do you think there's any change to this radius of convergence? Okay, so the theorem says that the radius of convergence will remain the same. Okay, convergence for. But why is it true? We won't prove it, but I think Yu Liang will prove it in his project. You can read his project later. So why you can do so, and then why the radius of convergence doesn't change. Okay. So we will see how we're gonna use this theorem to do some question here. So for example here, okay, try and determine the radius of convergence. Let's put R for this following series here. Okay, and find a closed formula for it when it converges. So first thing when you saw this, right, what should you do? What can you do? What can you do? The first thing you saw this. First thing you saw this, what can you do? How do we find radius of convergence before? How do we find radius of convergence for power series? 你想 lesser than what? Not quite right. It's the an plus 1 over an, right? You need to use the ratio test. Okay, you need to use the ratio test. So you make sure that the ratio of an plus 1 term over an is the limit is less than 1. But we try to use this theorem here. So can you relate this to different derivative of some function or integral of some function? Means some power series. Did you see any pattern with this power and this coefficient? Do you see any pattern? Can you observe the pattern between the coefficient and the power of x? Sorry? Kylan, what did you want to say? So the coefficient is 1 larger than the power of x. Okay. So there's a 1 differ by 1. Okay, differ by 1. So what can you do here? What can you guess here? You guess here. Actually, there are two ways to go. But which way do you think is obvious to you? Different people might think differently, but we can try and pursue your way and then see if it works or not. You want to try anything? Try? No? Like, who wants to try? Hi, Zing. Got any idea? Maybe we can look at the derivative of x plus x squared plus x cubed plus, and then so on. Okay, maybe we can look at this one. So are we allowed to do this or not? Okay, when are we allowed to do this? We can allow to do this if this series here has radius of convergence. Okay, do we know when this guy here has a radius of convergence or not? What is this? I mean, this is not quite, we have not quite of the example that we have seen before, right? What's the example we've seen before? That's closer, the closest to this power series. Now, what's the example of power series that's the closest to this x plus x squared plus x cubed? Plus 1. What's after plusing 1? What's this? I think this is the first power series that I disclosed to you, right? What's this? Joe? Okay, we know about the conversion of this guy. Okay, we know about the conversion of this guy. This guy converge when? For x that is less than 1 or greater than minus 1 and greater than minus 1. Okay, so we know that this power series here we can divide term by term. Okay, we can divide term by term by what? By the term by term by theorem above. But if you divide this term by term, what do you get? You simply get what? If you divide term by terms now. The first term you get 0, and then 1, and then 2x, and then 3x squared, and then 4x cubed, and then so on. Okay? Okay. Yeah. Okay. But on the other side, we have what? We also know when this power series converges, it has a closed form, right? What's the closed form for this power series? Geometry series. What's the closed form? What's the sum to infinity formula for this geometry series? First term over 1 minus r. So in this case, what do we have? Huh? X? What do you mean by x? X like this? X? No, right? So I need to speak precisely. What is this? What's the closed formula? Yeah, 1 over 1 minus x. Okay. But do you know how to differentiate 1 over 1 minus x or not? What is it? How to differentiate 1 over 1 minus x? Quotient rule. You need quotient rule? But no. Quotient rule, right? Differentiate type of function that looks like u over v. Right, so what's the formula? B prime u minus u v prime u minus u prime v over v squared. Okay, so what do you get? So you get what? Hmm? What do you get? Actually, you get what? 1 over y minus x square with a negative. Okay. But seems like my working is like backward. The backward. Things like backward. So so this is the logic of thinking. Okay, this is the logic of thinking. But when you present this calculation, right? You can start from the bottom to top. Okay, you can start from the bottom to top. So meaning you start with the series we have. Okay, and then when you go to the second step, like what I disclosed to you in the what in the start of the lecture, because due to we know that this power series here has a radius of convergence. Okay, we know that we can differentiate these term by term. Okay, we can differentiate these term by term so that these two equal, and then we know that this power series here has a radius of convergence, right? Within the radius of convergence, it has a closed form. Okay, it has a closed form, and then we can differentiate the closed form. Does it make sense? Okay, so although this is the line of thinking you should have inside your mind, but when you present it, you can start with this series that you are given. Should I write it once for you so that you know what am I talking about? So let's start with this. So let's start with what is given here. Okay, so this is equal to what? This is equals to the derivative of 1 plus x squared plus x cubed plus. Okay, why can I do this? Because we know that this power series is a geometric series that converges. Okay, so sum of n xn n equals from n equals to 1 to infinity is convergent. Is convergent where? For x absolute x less than 1. Okay, and then by theorem above. Okay, so we can use above theorem to do differentiation term by term. But we at the same time we know that within this the radius of convergence, we know the closed formula for this power series, which is 1 over 1 minus x. Okay, then we can do the differentiation. Okay, does it make sense? Okay, so this is the so here, let me not here. So this is the thinking process. Okay, and then here is the presentation. Okay, so this is how we do maths. Okay, how we do maths. We need to do it with with logic. So logic here means what? You need to know what you have, okay, and then what you want to achieve. So what's the assumption you have, so that you can use the theorem. But when you present, okay, but when you present your solution, okay, you can make it more. I'm not sure it's natural or not, but what do you think? What do you think actually? Not sure. What do you think? What do you think about the difference between these two writing here? What do you think? Maybe let me know what you think. Different people think differently. What do you think? What do you think? Maybe you see the equality, like you can go down, go back, go down, go back. But when I see this equality, right, there's a sequence, there's a flow. Okay. So if you follow the thinking process, right, from 1 to 2 is calculus. And then for the second line to third line is the theorem. And it's not a theorem, it's the convergence of geometric series. And then 2 to 1 is the what? Theorem. So I see with secant. Where's non-negative? And answer non-negative.
Positive.
Is it possible? I think it's not possible. So I did something wrong in the differentiation, is it? So which part? V prime U. So V prime U. U. So we do V prime U plus, right? And minus V U prime U. So V prime U. Anyway, so what's the formula? So what's the quotient rule formula? I forgot. Sorry? Use chain rule. Chain rule also can. Chain rule also can. So chain rule meaning you differentiate. Okay. Wait. Let me see. Wait, so what's wrong with my quotient rule formula? Is it correct or not? So let me write down. So d over dx of u over v is v prime u minus uv prime. Sorry, minus u prime v over v squared. Is this wrong? Wrong. What's wrong? The ballet?
Yeah.
The ballet?
Yeah.
I thought we have to the ballet. I forgot. Okay. So you mean like this, u prime v minus v prime u like that? Others, Agree. Can check. Agree. Okay. Because I thought it's different with product rule. Not different. Okay. No minus, then I think there's a calculation error last time. Okay. But anyway. So you think you see like this so that's me in my class I don't really care about the answer. I care about how you go to this floor. If your floor is correct, your final answer wrong, maybe 1 mark only. So in my class I care about the step and not the final answer. Okay, if you don't have step, you have final answer, you also won't get much mark. Your step is very important. Actually, it's logical. Final answer is not too important. This is very different from statistics. Yeah, because these people, if you put a little bit mean wrong, then your interpretation is almost gone already. Right or not? A large mean and a small mean is a mean different thing. So that's why those people are more computational. So different subject will focus on different aspects. And so don't mix up. Don't mix up. Don't compare this course with other courses. It's different. It's not comparable. Okay. Different profession, I would say. Different profession. Yeah. So any question here? Any question here? I want you to appreciate these two things. Starting from today, you should see these two things differently. One, you should keep inside your mind. The other, you should learn how to present your thing. Yeah, usually what's in your mind is different. I wouldn't say different, it's just the way of presenting. It's the same thing, actually, correct? No, it's really the same. But the way you talk to people is different. This will see even clearer when you go MA. We also do this kind of thing. We first find epsilon delta, and then we start by knowing epsilon delta first. Anyway, yeah. You will see it in future. Okay or not? So try to appreciate these two things. And then I think if you appreciate these two things, it will help clear out your mind and then clear out your thinking. When people confuse, I think it's this one. I think this one makes people more confused. Why you can do first before you know? Actually, no. Actually, I know first, only I can do. So I think this is why sometimes mathematics confuse people, because it's the way we present it. Yeah. So logically, it's I think no one should have objection for the top one, but the way how we write it could be quite different. Yeah. So next example. Next example. Similarly, try and consider these. Find the radius of conversion of the following power series: x plus x squared over 2 plus x cubed over 3 plus x4 over 4. Okay, so similarly, we do the same, find R and then find explicit formula. Let's see, what's my goal here? Okay, so let me just quickly do these exercises, not letting you to try yourself because I need to finish stuff today. So we will finish by an example of EX before we take a break, okay? I think we have 2 more at least to go. Right, so for this one, let's find R and explicit formula. So let's find a closed formula for this guy, okay? So remember, when I talk about closed formula here, only when this function is convergent, okay? If it diverge, you don't have formula, okay? Only when it is convergent. Right, so how about this case here? Okay, if you notice that you have division here, okay, and then you see that it's equal to the power for now. Okay, how do you recognize this? So you should think that when you integrate something, right, you need to divide by the power. So can you try anything useful here now? So can we try anything useful here? So if you try and guess, okay, actually this is guessing. Suppose we can use first. Okay, we work backward. So I put here guessing first. I think we guess first. So how we guess? Let's say we can integrate something term by term. Okay, so what thing I should integrate term by term to get this guy here? What thing get u and x if you integrate? What? 1 plus x. Oh, so you guess everything already. So 1 plus t squared plus t cubed. Okay, we change it to t because we want to integrate to x. So we guess this. When does this true? Theorem says what? When does this true? If the power series converge. Does this power series converge or not? Again, the same thing, right? What's this power series? Actually, is the geometric series. Okay, this power series actually converge somewhere where when t is less than 1. So your guessing is correct. Correct within what region? When t is less than 1. Okay, when your s lie between this region here. Okay, so your guessing is correct now. Okay. So can you integrate 1 over 1 minus t or not? Can you integrate it? How to integrate? I also don't know how to integrate. How to integrate? What do you get? Exam, what do you get? Oh, use substitution first. How to substitute? Y equals to 1 minus t. Okay, and then dy equals to minus dt. Then you should change your integration domain, right? So when t equals to 0, y equals to 1. When t equals to x, y equals to what? 1 minus x. Oh, y equals to what? This one. So we change it to 1 to 1 minus x of 1 over what? Y. Here we get what? Minus dt. And then what do we get? So you integrate 1 minus 1 over y. What do you get? Ln y. Ln 2 from 1 to 1 minus x. So what do you get in the end? Minus ln of 1 minus x. Ln 1 is what? 0. Okay. If you don't write all these down, can you straight away go from this line to the last line or not? Can you see the pattern? Can you see the pattern or not? It's a bit like chain group. And you can straight away jump if you like. Can jump. Yeah, I can jump. Can jump. Why you can jump? Why can you jump? I mean, when you jump, right, you should keep all these steps behind your mind. It's not about that thing y equals to 1 minus t. It's about how you view this 1 minus t as a function of y, 1 over something. Sorry, I didn't change one of this t. This is y. Okay, yeah, you can jump. Feel free to jump. But sometimes if you jump too far, you need to explain to me. Because if it's wrong, then you have no marks. Yeah, so about writing steps, right? So one very important is if you give answer without step, if it's correct, then maybe I will give you full marks. Okay, sometimes if I just ask for answer. But if you write down step for that question, but you calculate wrong in the end, I can give you marks for your step. But if you did it wrong and then you don't have step, then I cannot give you marks because I don't know how you get it. Does it make sense? So that's why I will always require to write step. Yeah, even if the final answer is wrong, then I can still give marks to step. Yeah, so that's why I focus on writing step. Does it make sense? For question. You go question. Then how? Clear. Yeah. So if you are not sure, just write down the step. And because if you answer wrong, you still have step. Okay. If the step is correct, obviously don't write bullshit. Don't bullshit step. Okay. Right. So radius of convergence will remain. Can you know where is the interval of convergence? So what's the radius of convergence here? This is bound by the property of geometry series. Okay, from 1 to -1. How about interval of convergence? So what's the difference between interval of convergence and radius of convergence? What else you still need to check? You need to check the endpoint. Okay, so what's the endpoint here? 1n minus 1. Okay. Why you need to check these two endpoints? I remember when you compute the ratio test, these two endpoints give you what answer? Oh, what's the limit of an plus 1 over an when you compute at endpoint? No, equals to what? What happens if ratio test equal to 1? Inconclusive. You don't know whether converge or diverge. So you need to check at 1 and minus 1. So can you quickly check when 1 and minus 1, what happened? Can we quickly check what happened if we have 1 and minus 1? What's the series we got here? So how about we just write here for convenience. So x equals to 1, what happened? What's the series we got? 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus dot, 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 dot. X equals to minus 1. We got minus 1. So it's actually a alternating what? Huh? Alternating what? What are these? Still remember or not? What's the first one? Sum of 1 over n. How many series? How many series diverge or converge? Diverge. Alternate? Huh? Alternating harmonic series. Diverge or converge? Converge. So alternating harmonic series is an example of what kind of convergent sequence? Absolute or conditional? Conditional, right? Because if you take the absolute value, it diverges. Okay, so the top one diverge as harmonic series. The bottom one converge. Converge by what test? By alternating series test. Okay. So actually you can find the interval of convergence also. The interval of convergence is what? Is minus 1 up to 1, not containing 1. Okay. So far, any question? I show you two examples where you can use differentiation and integration. Okay. How about I challenge you? I challenge you. Okay, I challenge you. Can you use integration method for the first example or not? Okay, go back and try. Can you use integration method for the first example? Or can you use differentiation method for the second example? Okay, see if you can do it or not. If you cannot do it, try and figure out why. What's the step you stuck? Why I cannot do it? Sometimes it's not because you cannot do it. Sometimes it's about the theory. Sometimes it's about theory. So I want you to play it out. Go back and play. Okay, if I gonna write, for example, this example as a derivative of something, can I work it out the series or not? Okay, if I want to write out the first example as an integral of some series, can I work it out or not? Okay, does it make sense? Okay, if you write it out, you start, okay, you can bring it to me next time, and then we can discuss. Okay, so then there are two exercises for you to look at inside this examples here. But I want to let you see one calculation here. So this calculation here, if you do this question tangent inverse, right? If you do some calculation here, you get a series. Okay, it's a famous series called the Leibniz series. Okay, this Leibniz series, if you evaluate at the endpoint, in that time, there's no computer. Okay, if there's no computer, how to compute pi? So many decimal points. Okay, so this is one of the way to compute pi. Okay, because we can write pi over 4 as some series. So you can imagine I multiply 4 to the other series, then you will get pi. Okay, so the old people have used a lot of way to find pi. Okay, so this is one way to find pi. The other way to find pi is you start with a circle And then you start with polygons. Yeah, you make more edges to the polygons to approximate a circle. Can you imagine or not? Okay, you start with a circle, and then you put a triangle inside the circle, such that the vertices touches all the, the vertices lie on the circle. And then you add one more edges, square. Can you imagine that the difference between these polygon and circle becomes smaller? Can you imagine or not? Try and draw it out. And then you can make pentagon inside the circle. And then you keep adding edges. And gone, and polygon, infinite gone. So we realize circle as an infinite gone. Taking limit. Yeah, no? Yeah. This is one way how the Chinese people learn pi. I mean, people in China, ancient China. Yeah, ancient China. Similarly, for Archimedes group of people, how they learn it? They put circle inside a gone. So we approximate from outside. It's a similar idea, right? We approximate from outside. Meaning what? For example, I put a circle inside a triangle. And then I put a circle inside a square, a pentagon. So one type of people approximate circle from inside. The other type of people approximate circle from the outside. So this represents different viewpoint toward maths. And we should take all of them together. Okay, we should unite all these ideas. Does it make sense? Okay, so as long as your working makes sense, it's correct in mathematics. Okay, so we don't discriminate people. Okay, as long as we work to the same concept, not concept, same goal. Okay, yeah. Just that sometimes we can't how to say, we can't understand what others people think, what others are thinking. So there are few responsibility here. So you need to, how to say, learn to express your own viewpoint. And then the other thing you need to learn is listen to others' viewpoint. That's why you are given a mouth and an ears. So you have to use them. Okay, use your ears, use your mouth properly. Okay, so before we end, there's very important exercise we need to do before we end this hour. So this very important exercise is this one. So let's write it down first, and then we'll discuss. So let's find. So this question actually is very straightforward, but this is a very important example. And so this exercise is very straightforward, but it's a very important example. Find a formula for this series. So this is the next important series after geometry series. Okay, so this is very, 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 very important. Okay, I think we met this before. So we talk about this coefficient here. We say that this coefficient here converge to 0 pretty fast because this n factorial grow pretty fast. So this n factorial grow pretty fast. Okay, grow pretty fast. So what's the closed form here? Since it converge, right? We should ask whether there's a closed formula or not. Because it converge. Okay, how if it has a closed formula, how do we find it? Okay, how do we find it? So we're gonna use the ODE trick here. Are you guys taking ODE or not? This semester, huh? Okay, good. So we're gonna use the ODE trick here. So what's the ODE trick we can use here? Huh? Differentiate or x, yeah, okay. Okay, so you actually observe that the derivative of x is actually x. Okay, so let's write it down. So not that one. Before we had already compute the radius of conversion for this guy. If not, you should use ratio test again. So where is converge? Anyone still remember or not? This is the first example I gave you such that it converge everywhere. Okay, using the ratio test. So if it converge, then I can use the theorems. Okay, I can differentiate term by term. Okay, so imagine if you differentiate term by term, what do you get? What's the first term you get? 0, 1 plus x plus x squared over 2 factorial plus x3 to the 3 factorial. So you can see that it's just like shifted x again, okay, with an additional 0. So it doesn't matter. So it's really just, sorry, here is x prime. It's really just x. Okay. Have you guys learned separating variable? Learn? Okay, so what can we do here? So time for non-proper max. Actually, separating formula is just a formula. You need to prove it. So let me put here. So separating variable. So I wouldn't say this is a max. I will say this is a method only, calculation method. Actually, you need proof this one. Did who teach you all the Did Basta prove to you why it works or not? Huh? If not, go and ask him again. Okay, ask him why it works. So how you use it? So we're just gonna use it. So d of dx of x prime, so fxx equals to xx. So what's the separating variable do? So Basta will tell you put dx to the other side, right? Okay, and then you integrate both sides. Okay, so what's this calculation here? Are we ready to integrate? So I think we should move xx to the other side also first. Okay, so that why is it separating variable? So you can see that there are two variables inside here. One is x, one is xx. And two variables here. Okay, so one side only has xx, the other side only has s. Okay, so this is what called a separating variable. You are separating the variable before you integrate. So what do you get here? This implies what? Implies what do you get here? Do you know how to integrate this function? Maybe I put it longer, maybe it's easier to see like this. How about this? Is it easier to see what do you get? Or maybe I add one more thing here. Is it easier to see what you get? Yeah, these are the same thing actually. You need to get used to these things. Because typically we don't write 1 anymore. It's like 1 times x, we just write x. Okay. So what do you get? Ln of xx plus x plus some constant. And then you will get e to the what? E to the x plus y on the other side. And then one side we left with xx. Okay, or we simply, since e to the c is a constant, right, we will replace it with another constant. So what to do here? What's this constant here? Can we fix some constant here? Yeah, so can we fix some constant here? Do we know any points here? Okay, do we know any boundary condition here? Yes. So if you put x equals 0, what happens? We know that x0 is 1. So since if you sub x equals 0, we get 1. So we know this boundary condition here. So this means what? 1 is equals to a times e to the 0, which is a. So a is just 1. So this implies that e to the power x is this power series here. Okay, so this is how we get the power series representation for e to the power x. Okay. Yeah. So actually, how we define this exponential function, right? Actually, it's through this ODE here. You ask yourself, is there a function when you divide, you get back yourself? E to the power. How do we found it? Actually, we found using this power series first. Only then you have e to the power x. Okay. Yeah. Okay, any question? So e to the power x is the defining property is this one. Is the defining property. When you differentiate, you get back yourself. Correct or not? Your high school teacher tells you differentiate ex, always get ex. It's because how we define it. We define it that way. That's why it is like that. Yeah, you can go back and tell your high school teacher now. We define it like that. Okay. It's not formula because we want it to be like that. Okay, any question? So very important. This one is the next important power series example, other than the geometry series. Okay, e to the power x. You have to almost remember this guy. Okay. If you forget, then you go back and think about how to satisfy this derivative condition here. How can you make sure after you differentiate, you still get back yourself? It turns out that you need to put that factorial thing. Why you need the factorial thing? Because you are differentiating a power series. You need to bring the power down. And then, yeah. So to make all this work, you just put n factorial as your coefficient. Or divide by this n factorial. Okay. Okay, so let's take a break and then we'll come back with Taylor series. Let's break until 10:17.哦，我没有这个 n 诶，我就是看那个我是从一开始，我应该没有写错，我看一下，我故意这个有点不一样，因为这个你是看呀，我是从一shit，sorry，我加了这个 n，但是我一是对的，诶，没有错啊，我加 n 也没有错啊，我想一下，加 n 有错，不可以以为，
那是 n
但是是从一开始，因为我要写的是这个人嘛，
这个人，
也对，这个 n 是多少？
他应该是从零开始，然后从上面是 n。
哦，
对
你要
诶
，I mean 都可以，但是这个 form 是我们一开始看到它的时候，也
这个对是这个，
也
是
诶，这个就是那个 geometry 是
在前面。
零吧，因为有一个零嘛。
什么意思？
啊，对啊，从零开始，n 从零开始，x 也是
哦，少了一个哈，n 减一是吗
也是。
？OK confusion，sorry，
哦，这样子它的那个 radius 跟它是一样是一。
对，所以就是一。你其实可以看它的 interval conversion 也是，去检查。 跟你讲，我 break 到几点忘记了。到17啊 ，OK。
好的 example
嗯
给这个 define
嗯
它是 increasing 的，
好，
那我可不可以用就是先就是如果 x 小于 y，这样 f(x) 要大于 f1，然后我来就是反证这个东西，因为我算到就是 x 大于 y，可是 f(x) 也大于 f(y)，所以我就讲说它不是decreasing，
你是说它永远还是它有些点？
有些点，因为这个的
OK
话它是可以啊，可以用那个 definition，
对啦。哦，你是说哦，
还是我要用这个继续用这个 mean value theorem？可是如果用这个话，我必须证明这个东西是 differentiable。来到这里我就不能
喂，等一下，你的意思是说要讲解释你的东西是 increasing 是吗？
就是我要讲，因为我现在已经证到说这个 sequence 它是 decreasing 的，
对，
所以我要讲这个 differentiable function。
不一定是 decreasing，
对
所以你现在要说的有些 part 是 increasing。
对，
嗯，然后你是说either我要用 derivative 来说，还是要直接可以从 definition 开始说？I mean 从这个 f(x) 大于 x(y)。你们 calculus 要教什么？这都有教吗？
明白就
不是，I mean for increasing decreasing 这种，它是直接教 f(x) 大于 f(y) 还是它教 derivative，还是两个都有？
好像是有，然后这个
derivative 用 derivative 来检查有没有效，
也是
也是有的。因为他们是 equivalent 的，其实。
可是如果我用这个 f x 小于零的话，这个我要 differentiate 这个东西哦。对我想到的 definition 只是说就是
如果 differentiate 不了，不是这个的 example 了。
这个 differentiate 只是很难记。
能力有啥子啊？AI 可以用另外一个
可以啊
AI，
OK，
可以都可以用，对
OK，
反正考科什么有讲过。
然后还有就是我需要分个 function 这样，我题目
但是就算你不 differentiate 它，你应该要 comment 一下为什么要 differentiate 吧？一点哦，可能容易看是什么 anyway，就是 converse 还是怎么样。你能够画出你这个课吗？能画出来比较好，
画出来了。
画出来比较好，不要直观。
好，
画出来了，然后我们可以怀疑它是不是 differentiable，我们再去看它的部分。
一个东西就是我需要在这个 different，因为我的 mean value theorem 它是讲这个东西是 continuous 的嘛，
differential imply continuity 哈，
看选择吗？
非常好，有很多人在问了，这样我要讲一下，可以用，可以用，可以用，可以用，可以用，可以。Everyone here? There's 箭头 not here. Never mind. We wait for 箭头。Okay, maybe we will discuss first. Okay, so I think quite a few of you noticed there's a gap you need to fill in for your assignment question. Which question is that? 1. Okay, question 1. That you require differentiability implies continuity to use mean value theorem actually. Okay, you can assume that. Did you guys prove that in calculus 1 or no? Prove Proof or just mention? Mention only. Differentiability implies continuity. Got proof. Yeah, you can use that. Okay, you think even don't prove even if he didn't prove it, he should mention it. Differentiability implies continuity. That one is for one variable, so you can use it. I think later we will have question on two variable to check differentiability implies continuity. I forgot, but seems like you will have it later. But you can assume it. Okay. And then for that, I think, did you guys figure out you need a counter example for that question actually? So for that counter example, right, I recommend you draw your example first. Sketch your example. Okay. And then you can produce a formula for your function. Most probably you need piecewise function. I'm not sure you can do it without piecewise or not, but if you need piecewise function, maybe comment a little bit why is it differentiable or why it is satisfying the condition inside the. Maybe you don't need to go into epsilon delta stuff, but try to explain a bit. Okay. Gentlemen, you just back. Yeah, Humble is here. You can try ask Humble how to prove it. And we mentioned that you can use the assumption that differentiability implies continuity for question only. Okay, and then try and draw your contact number for that question. And then write down the formula for your function that you define, and then try and explain a bit why it satisfies maybe differentiability or other property that the question needs. Okay. Obviously, for my assignment, right, you can go full reversity. Okay, you can do that. Okay? You can do that, but we try to keep minimal thing. For example, we want to skip epsilon delta argument. Okay. So this is the principle. If there's no chance to skip it, I will try and figure out a way. Either I give you the hint or either I let you assume it. Okay. Yeah. So if you met this kind of epsilon delta argument, maybe you can ask me whether you need to produce it or if not, producing it. So how we go about go around it. So it's good that you keep thinking about this idea, okay? Because these kind of gaps is waiting to be filled in MA. In MA, we will fill all these gaps, okay? Such that there's no gap. Okay. All right, so let's do an opening example here. So we really want to link stuff to geometry. Okay. We really want to do geometry, okay? These are about analysis, algebra, all of these is about geometry actually. Is it true? When you live inside, when you wake up every day in the morning, did you see number or did you see object? You really see object. It's not number. It's not derivative. It's not integration. Correct or not? It's actually table, chair, trees, sky, rain, or maybe sound. Later we'll learn sound for a series. Sound. Okay. So these are about geometry. Okay, but we try to make it into some number that we can play around. Okay. So how to link analysis to geometry? So again and again, first example, you cannot forget in your life one. Okay, is this a geometry series? So how to think about this geometric series geometrically? Okay. So to think about this, right? We can split out all the terms. Okay, we can split out all the terms. For example, do you know how to sketch 1 over 1 minus x? In which level you learn this sketching? Which level you learn how to sketch this function? Who teach you to sketch this function? Who? What? Me, meh? Oh shit! I have to start all over again. Huh? I can start all over again, but any moment you learn this, which year? Last sem, just last sem. So your high school never sketch graph? Huh? Huh? Oh, nowadays teacher use Desmos to teach. Okay, I think high school got sketch simple graph. And then at A level, I think I also got teach. Yeah. So I mean you need to know how to sketch basic graph first. And then you will learn how to sketch the graph that gets shifted. Okay. So how do you view this 1 over 1 minus x? You should view it as a basic graph like 1 over y like that. So 1 over y, how to sketch? It is just, okay. I think 1 over y is not as basic yet. So the basic one should be y equals to, I mean, constant is the easiest one, for example, right? Y equals to 1. Okay, let's do it one by one. Okay, so let's do it one by one. So this is y equals to 1. In particular, this one, this guy is y equals to 1. Okay, let's say this point is 1. X, y equals to x is the next easiest one. Okay, we call the identity function actually, which is this line. Why is it identity? Because you link the x equals to 1 to y equals to 1 like that. And then similarly for all the points, that's why you get this diagonal line. Does it make sense? Make sense or not? So you send 2 to 2 also. From here, I think we can talk about 1 over x. So what happens if you do 1 over x here? You can check point by point. For example, what happens to 0 point? Actually, not defined. Okay, not defined. So not defined, we can keep it first. We can look at all other points. If you look at all other points close to 0, what happens? 1 over a very small number is a very large number. Okay, it's a very large number. But when your denominator gets larger and larger, your 1 over x get smaller and smaller and smaller. Okay, so that's why if you look at 1 over x, so let's put here. This guy's okay, so what happened on positive side, non-negative side? You go from very large number to a very small number. But you still stay in first quadrant. Why? Because you are always positive. But you also never get 0 on the other end. Why? Do you know anything that you can divide such that you get 0? Also not defined. Okay. So you will avoid the two extreme here. How about on the other side, negative side? You will notice that you always stay in the third quadrant here. Because if you go to a negative small number, you will go to a negative large number. Okay? But at 0, don't know. Cannot define one. So that's why whenever we write this y equals to 1 over x, we will add another condition. S cannot be equal to 0. No point there. Not defined. Okay? That's why we put an x not equal to 0. So this condition here is really, 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 really important. Because you really cannot find anything here. And nothing there. Does it make sense? Okay, but this question is about 1 over 1 minus x. So how to build 1 over 1 minus x? First, what can you do? Add this minus first. Or not? Is it true? Yes, we can add this minus first. So add this minus, what happened? What happened if you multiply a minus to your function? You swap. Okay, how I swap? Correct, right? So swap like this. And then you shifted by 1. How to shift? Meaning what? The 0 point become 1. Okay, so you shift to the right. So what's the y-intercept here? Y-intercept here is 1. And then the asymptote become where? Where's the asymptote? X equals to 1. Sense? Okay, so this is 1 over 1 minus x. Okay, good. So this is 1 over 1 minus x. All right. So we have looked at 1x, 1 over 1 minus x. 1 over 1 minus x. What else we have to look at? S square. S square, you know how to plot. X square, and then x cubed, and then S4, and then x to the power 5, snake again. So actually you alternate between this snake, a snake, and a, what's that bola? Hyperbola or parabola? Parabola. You sure? I think it's a hyperbola. Hyperbola? Hyperbola or parabola? That shape. Huh? Hyperbola, right? Is this what you learn in algebra and analytic geometry, that course? Yes, okay. So this is called a hyperbola. Okay, hyperbola. Right. So, hey, look at here. So last time we said that this power series, right, is the expansion at x equals to 0. So how you relate this sum to that curve there? Okay, how do you relate that sum to that curve here? So let me remove all these. Okay, so we bring this guy. Okay, now I think you go back, you can use Desmos now. Because Desmos is more accurate than me. Okay, so we zoom in. So zoom in at the point that this power series centered. So it's centered at where? So let me put here. Centered at 0. So meaning, let's look at what happened to this function at x equals 0. So we zoom in. So let's zoom in. Zoom, zoom. So let's draw this part larger. Like this. Okay. Zoom in. So let's zoom in, then maybe I put a scale here. This is 1. Okay, so this is the 1. This is the asymptote 1. Right, so what happened? Okay, we look at term by term here. What is y equals to 1? Okay, y is equal to 1 is this line here. Is this straight line here. Okay, is this straight line. 1 plus x. Hey, question. Para or hyper? Wait, let me check. Wait. Let me check. Parabola or hyperbola? Okay, parabola. So this is parabola, don't confuse that. But anyway. So what is hyperbola? Let's draw hyperbola also. So that people will know how to differentiate these two. Okay, so hyperbola is the other one. So hyperbola is something like this. So why you learn these things together? Because you learn it as a cross section of conics, right? Okay. So what's the cross section of conics? If you cut it this way, right? Then you will see the hyperbola. Okay, hyperbola, you see you can cut it this way. Slanted line, right? Vertical, you might get this. Okay, anyway, so you should go back and check. But my point is, if you look at y equals to 1, you'll see this constant line. How about 1 plus x? So we know that y equals to x is like this. 1 plus x means what? You need to shift your y equals to x up. Okay, so if you shift it up, then you must see something like this. 1 plus x. Y equals to 1 plus x. Okay, let's order this function. How about x squared? 1 plus x squared. Does it have a root? Does it has a root or not? How about 1 plus x squared? Does it has a root or not? B squared minus 4ac. Yeah. So 1 minus 4 times a times 1. Doesn't has a root. Okay. No real root. Surely, no real root. Do you know why? You know why? Where is this graph lies? Above. Yeah, it's not intercepting the x-axis. Okay, good. So correct, there's no real root. Okay, but where is it? Actually, it is somewhere here. What's the y-intercept, for example? 1, correct now? If you substitute x equals 0, the y-intercept is 1. But actually, you can check that y-intercept should be the minimum point. So your y equals to 1 plus x squared. Okay, so maybe I draw a little bit wider because since we already zoom in. And then s cubed, So you will see that if you add higher and higher term, the general shape will remain. So what's the next general shape? So the next general shape is y cubed. Any more color I can use? So you can see that the next general shape is this y cubed. So y4 equals to 1 plus x squared plus x cubed plus x squared. Okay. If you go and use your GeoGebra or Desmos, go and plot it out, you can see that this function, right, will agree with the original function on a wider and wider interval. Okay, wider and wider interval. Can you imagine or not? What's the difference between x squared and s to the power 4? The bottom getting wider and wider. Flatter. Maybe we don't call it flatter, just Wider also feel very weird. Fatter, fatter, yeah, fatter. Do you mean what? Do you know what I mean by fatter or not? So you can see that y square looks like this, okay, and then you can see that the y, if you has sorry, this is x squared. If you, for example, you look at y equals to x to the 100, okay, what do I mean by fatter? So it means that when you get closer to x equals 0, what happens is getting closer to y equals to 0. When x get closer to, sorry, let me rephrase. Let me rephrase it. So let me draw first, and then I'll rephrase it. Okay, so you will see that the part that is around 0, okay, there are more y value getting closer to y equals 0. Does it make sense? When you have higher and higher even power. Okay, when you get when you look at all the x around 0, there are more y value which is closer to 0. Okay, so this is what we mean by factor. So you can imagine that this factor part, okay, this factor part will agree with this 1 over 1 minus x even more. Okay, if you don't believe, go back, use your GeoGebra or your Desmos, okay, plot all these functions together and then zoom in, okay, zoom in. You will see that if you add more and more higher terms, you will agree more starting this at the center here. This center here is x equals 0. That's why we call this power series center as 0. It always agree at 0, right? Correct or not? If you substitute x equals 0, all terms you'll get 1. Agree 1. So it's like you agree at that point first, and then you start and grow your function. So how about that thing? Agree up to x in between 1 and minus 1. What does this mean? So the at most the interval you can agree is from 1 to minus 1, strictly in between. This is the most interval you can agree. Away, you see, away from these 2 points, you see, deviate very much. A lot. Deviate a lot. On the other side, also a lot. If you go beyond this 1 and less than 1, deviate a lot. Okay, now. Can you see from geometry now? From algebra, we proved to you, right? It diverges the sum. But from the geometry, you can see that the function will go. The difference between the blue line and all the other color will be getting larger. If it is away from, even at minus 1 and 1, and then strictly larger than 1 and strictly less than 1, minus 1 is the same. Okay, so you need to realize on this factor part. Actually, this factor part really important. This factor condition also happened in the odd case, right? Can you imagine or not? What happened in the odd case? The odd case also you have this kind of phenomenon. So if it's y cube, you have this snake sketch. But if you go, for example, 101, what happened? 101. Okay, you can see that when you get closer to 0, there are more y value that get closer to y equals to 0, like this. Also kind of get factor. Meaning what? Meaning it decreased really fast. And then when it got to 0, it gets slow. And then if you move away from 0, it gets really fast again. Does it make sense? Understand? Okay. Yeah. So actually you rely on this factor condition to match up your original function. Okay. Imagine, so this is what Taylor series do. Sorry, this is what this power series do. What time is it? Okay, 10:40. So we're going to introduce this phenomenon here. So before we calling it some special name first, let's have a theorem first. So if we can write F as a power series representation, okay, so it's a C what? C n of x minus a to the power n equals to 0 to infinity, okay, at some radius of convergence. Then actually we have a way to write this power series down. Okay, there's a formula to write it down. Right, so there's a formula to write it down. It's actually the n derivative of f evaluated at the center divided by n factorial. So there's a formula to get it. Okay, so now previously I just told you there's some coefficient attached to this monomial. But now I tell you where these coefficients come from. Okay, they come from some derivative of your function. Some derivative of the function. Okay, so these coefficients are special. Can you verify this or not? If you have this form here, do you know how to get your coefficient from your f? Okay, so one thing I want to remind you, because you are learning mathematics, I will say that you are lucky. Why are you lucky? Because you got a textbook. When we do research, we don't have textbook. The real life question will ask us, what is Cn? They won't tell us Cn equal to this. So when textbook tells you Cn equal to this, meaning what? It gives you a way to find Cn already. What do you need to do next? You just need to check. Why I say you just need to check? Because you already know what is f. Do you know how to take derivative? So that's the only thing you need to do on this right hand side here. Okay, so let's verify one by one. Okay, so let's verify one by one. So if you want to prove this, meaning you need to prove for all n. So if you want to prove for all n, just start from the basic n first. So what's the basic n here? Is 0. Okay, so you want to check whether C0 equals to f of 0 evaluated at a over 0 factorial or not. But what is it true? What is f0a? F0a is simply fa. 0 factorial is 1. But what is fa? You know f, right? So you substitute x equals to a. But what do you get? What do you get? So this is your question first. So what do you get on the right hand side? What is fa? You simply substitute into your power series representation of your f. So which is a minus a. Maybe some of you will tell me this is 0. Is it 0? Dangerous. Really dangerous. Is it 0? Dangerous. Huh? If it's not 0, where's the calculation goes from? Dangerous. Huh? So when you look at this sum, you really need to split it up first. What does this sum really is? This sum is what? Do you remember? What's the first term? Huh? C0. Go x? No, right? And then C1 times a minus a plus C2 times a minus a to the power 2, and then so on. So is it 0 or C0? What's the sum left here? It's actually C0. Okay, because the first term here, there's no factor of A minus A. Okay, so you need to be careful when you evaluate this sum here. Correct or not? Even if you look at here, this guy start with 0. Okay, so already disappeared. Before you substitution, already disappeared. Before substitution. Correct? Before substitution, already disappeared. Does it make sense? Okay. So you left with the constant term. This is the term not multiplying with 0. Okay, so you really get C0 actually. Does it make sense? Okay. Any question? Or question or not? No? Clear? Okay. How about C1? How about C1? So C1, you need to just compute what is F1. So let's compute it quickly. So F1A of n factorial. Okay, so how to produce the first derivative of your function, yeah? Can you differentiate or not? Power series. Can you differentiate? How do you differentiate? How do you differentiate power series? Last hour. How to differentiate? Term by term, good. Okay, term by term. So when can you differentiate term by term power series? When it converges. So we have a radius of convergence here. Okay, so we can differentiate term by term inside there. So when you differentiate term by terms, what do you get? What do you get? So the first constant term will disappear. Okay, what do you left with? C1 and then plus, oh, here become 1. C1 plus C2 times what? Times 2 times x minus a plus C3 times 3 times x minus a to the power 2, right? You differentiate your power minus by 2 by 1, and then so on. And then we need to evaluate this at the center. So what do you left with? You can see that all the term with factor x minus a become 0 again after you substitute your center. So what do you left with? You left with C1. Okay. Maybe do one more, and then we'll see some pattern here. Do one more. So if we do again for second time, okay, what do we get? You see that we get 2 times C2 plus what? Continue differentiating that guy. So your C3 will multiply with what number? C3 times 3 times 2. Okay, and then the power reduced further. And then what is C4? C4 have what? Times 4 times 3, and then power left with 2, and then so on. Okay, and then you need to evaluate this with x minus a. Okay, so same thing. All the factor with x minus a will disappear. Why? Because you have a minus a. So you just left with 2 factorials times 2 times C2, which is just C2. Okay, so can you realize where this n factorial formula come from or not? Because each time when you differentiate, the power will become the coefficient. Okay, does it make sense? Okay, yeah. Any question? So this n factorial here really come from the differentiating the power. Can you see the pattern? If you cannot see, write one more. F3. Okay, still cannot see, right? F4. And then you will see it. Okay. Does it make sense? Okay. Very important, this formula here. So what? So we will define. So now, so let's define this function here. So let's define. So definition. The series written as the sum. Okay, let's not write as a big sum first. Let's spell all the term. So the first term is you evaluate f at a, and then the second term you differentiate f at a, and then you divide by 1 factorial, okay, and then multiply by xa plus f prime prime a over 2 factorial times x minus a squared, and then plus f prime 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 a over 3 factorial plus, sorry, multiply by x minus a cube plus so on. The series is called the Taylor series of f and x equals to a. Okay, so we have so what have we done so far? We learn series first, convergence series, and then we study a specific series which we call a power series. What is power series? You have a coefficient multiply with your monomial, right? Power of x. Now we go into more specific. This Cn, we control the Cn. How do we control the Cn? This Cn comes from the n derivative of f. Okay, more specific Cn. Okay, and then this, with this Cn, this power series is called the Taylor series of f. Why is it of f? Because this Taylor series really depends on f. Why? This is how we get the coefficient, the n derivative of f. Okay, does it make sense? So another definition was the Maclaurin series. So what's the difference between Taylor series and Maclaurin series? If s equals to 0, then it is called the Maclaurin series. Okay. So the difference is where you expand the point. Maclaurin, how to spell? Maclaurin series. Okay. Maybe one thing you can pursue in your project is which one comes first? Does Taylor series come first or Maclaurin series come first? Or why there's two different names? Okay, for in principle the same thing. Okay? Or is it because that Maclaurin studied these kind of function in different motivation? Okay, or Taylor studied the generalization of Maclaurin series. So whichever comes first, you can try and go and look for it. Okay, the history. And then you can talk about how they use these things in your project, if you like. Okay, so before we finish, maybe we find a Maclaurin series first, and then we can continue after the break. So let's do one example. So let's find the Maclaurin series of the function fx. Okay, so I also can rephrase this question. I also can rephrase this question as find the Taylor series of the function at s equal to 0. I also can phrase it like that. Okay, it's the same thing. It's about the center. Taylor series is about general center. Okay, but Maclaurin fixed the center at 0. Okay. So let's find Maclaurin series first. So what's the strategy? Still remember what's the Taylor series definition? We need to determine the n derivative of f. So what's the n derivative of f? There's a reason why we pick ex, right? Why 尖筒了? Huh? What?
Theorem of x and also to prove that equals to ex.
No. I mean, not about that. It's about this Macron series. So I mean, okay. So by definition, what do you need to figure out this Taylor series here? You need to find all the coefficient. But how you find all these coefficient? This is just what? N derivative of f. Okay. But what's the derivative of ex? Itself. So let me write these down. So what's the ingredient to make Taylor series? You need to compute all the Cn. So what's the formula of Cn? First term you have f evaluated at the center. Second term, first derivative evaluated at the center divided by what? 1 factorial. And then second derivative divide at 0 divide by 2 factorial. And then you keep going. So you need to have infinitely many of them. In principle, this is very hard to do. In principle, it's very hard to do. You need to do it infinitely many times. 1 million also not enough. You need to go infinitely many times. But what do you know about EX? So what do we know about EX? Just now, the past hour I told you, right? The derivative of EX is always what? EX. Okay, so no matter how many times you differentiate it, you still know what's the derivative of EX. It's just EX. So this is the nice thing about this EX here. Okay, so that's why this EX become the first example. Okay, because it's very easy to compute it first derivative. So in this case here, you can easily see that all of these are just e to the 0. But the Cn here will have some scalar condition, right? So you just have some scalar condition here. So in principle, what do you get here? In principle, what do you get? So size. So from the property of Ex, you can infer that f to the n derivative at 0 divided by n factorial is just what? 1 over n. Okay. Okay, no. So what's the Maclaurin series for Ex? So we just piece these coefficients together. Okay, so we just piece these coefficients together. So the Maclaurin series for Ex is what? Is 1 plus, what's the second one? 1 over 1 factorial times x minus 0. So it's just x plus 1. 1 over factorial times x squared plus 1 over 3 factorial. One over 3 factorial times x cubed, and then keep going. But what is this? What is this? I think we saw this before, right? Yeah, we just computed just now. So it turns out that what we computed just now is a Maclaurin series for Ex. Okay. And then what do we know from just the proof that we did an hour ago? We see that they are equal. So in general, we need to show that Maclaurin series were equal to our function at a radius of convergence. So how do we do it generally? This is the problem that we need to solve in this section. How do we show generally the Maclaurin series will agree with the function at the radius of convergence? Okay, so this is the question we're going to solve in this part. Does it make sense? Okay, so it turns out that what we did just now was a Maclaurin series for Ex. Okay, so we try to generalize these to general function. Okay, general function. Okay, any question? Any question before we break again? Question? Any question? Any question about the idea gonna do next, how to connect what we did before and now. Okay, so if no question, then let's break until 11:10.
要提这个一个给电话，我们两个都连我觉得可以用好的用。哦，他好那个是，这个哦，是不是感受？我的点头手这个方向完全没有错，或者的话不给你用，那先不用。要去啊！我说客服，我讲话的话，大家知道的。不要比赛，是在快乐网上好笑，
还是要用 X 买？
那有意义没有？镜子吧。
哎，没有，昨天我按了，它确实是会跳切那种啊。但是如果我没有钱，我就玩不了。对，但是你可以选，
你可以选两个
啊，你可以选两个，但是你选手臂，因为它不给你扣了，因为它就是要你用本
啊，这个
它就是点 S，你如果换手臂，它没有给你看。
拿来 S 的，然后我给你不知道为什么，对我有错吧？那你就我该没人用，
大家有人用这种方式，有人用。
那我是有这个，买的这是都有的，我就你不懂，我跳反，他帮你跳反，数据也不长，你还不知道的东西。这种有没有人拿上给去把车推过好的？很帅。对啊，
基本上就是 left right 的 purity。好像跟整个有不这样子。你要看那个 gradient，我不知道。但是你的方圈不能直接看出来的 difference，你的方圈不能看。
没有啊，就是这种这种非常大的那个荧幕屏不停看一年的，变成什么日本？你们哦，你把你可以，那因为你把它不是导出来一点，可以讲那个里面的，你不的还是知道。确实，知道不知道？我在那边看，我不想问，我现在有些可变上课了，那不是一个啊，我操，别放生，没放死。对对，你们 这张专利就没有智能的。这我是出钱了，你这边要本地。我也是提醒的，并不来的。我说我是把它们在一起的，我说放在一起的。不是感冒，我因为在生活上的这种的时候，就是导致
哎，
水分不足了，但是。有些，你看有个no problem 是有没有问题？然后呢？没有现在算一天一天买一天，他们给嘛一天哦，
你们需要 extend 吗？Simon，
现在
需要 extend。
全部会同时讲 extend 哦，老料老料不？
对没有 extend 多久？
一个礼拜。原本这个
给你 extend，多少？
对，给这个这件，他在反正 extend 就下个星期见了的。他在 conversation 在别的房间。我做你要在 AA 电讨是吧？
你们要 extend 多久
？extend 多久？什么问题？extend 多久啊？今天几号？今天10月10。11加1等于2吗？加2天啊？1加1等于6，好，可以，这个好，这个好，还要是。
你说好一点。
你用那个星期？
明天。
好，明天6啊，可以了，可以，我明天就给他们找人了。我是懒惰抄那个时候，还没有做啊，是，还不是 draft 版本吗？明天
啊，
明天不是 draft 版本吗
OK
有人猜一下，对，有人猜吗？可以啊。
哦，你要比赛哈？那你比赛明天也没有用，不是？你都比掉整天了。
你到用吗？你到6点。
所以你
晚上还有时间，考试给你定了时间。啊？没有啊，还有2个小时做完，你还上。
这样厉害？
考试它不一样是，所以我那天讲了，考试是吧？卷子给它是另外，我们是另外。
他一样，我们一样，还有1个小时给。他只1个小时，还没有换结。
我出不来都讲。
明天啊，你要明天，你明天可以吗，Isaac？你明天可以？OK。哎，可是只有他去比赛哦，你们没有比是？
我给的。
所以只有他去比啊，这个班没有人去比啊？有人去比吗？Simon Marais 没有，数学比赛没有，你不懂，因为你不懂的，不知道。到我们学校有举办一个 Simon Marais 的比赛，它是一个全球的数学竞赛，for undergrad 的。没有选拔，想去比就去比，呀、就 I mean 就自由去比哦，没有什么，你有名就有名哦，没有名就没有名。你不懂，有兴趣吗？你们啊？什么？全球的，全球的，你不懂？它是每年一次哈，每年哦，明年还有机会啊。Next department 的 teams。
Hi, your assignment is we submit assignment. 他的 assignment 都 blank，大家submit 的是。
OK，什么叫很多 blank？
是你的那个 assignment PDF 是。
周末会这样？之后我没有遇到过
我是给他的
，size 不一样。哦， OK，
去改它。就这样的，你压力，
tak boleh tak boleh。
人家跑掉呗。
没有，我没有很想吵，只是人家要跟我吵的话，我不是跟他吵咯。
手机的
啊，
记得搞掉。
看我，
哦，你还在 record 着？
我没有问题啊。是你讲他名，我没有讲他名。我没有讲他名。Right. Yeah. So there's a Simon Murray's competition you can join annually. And every year you can join, or you. What's the 3-year rules? Last time talk about. Consecutively or what? Or in your lifetime? Lifetime or you only got 3 chances? Oh, only for undergrad. But your undergrad only have at most 4 years, but I think unless you fail. No, at most 3 that's why they restrict to 3 times. If you keep failing, you also only can do 3 times. Yeah. So for the lifetime, you can take part 3 years, 3 times, 1 times per year. Only for undergrad student. Yeah. You can go get experience first. And they I think they organize the discussion about past year question also during the student group. Student what group? Study group. Max study group. When's the max study group again? Monday, Wednesday, Friday. Where they announce. Oh, family teams. In IG. Which IG? What account? Student council account. Okay. Yeah. So you please take note of these notices. If not, you ask him also can, Isaac. Yeah. If you're interested, next year, join again. This year, I think passed already. Okay. Right. Yeah, let's continue. Right, so what's our goal just now? Our goal just now was to show fx is really equal to its Taylor series. Okay, Taylor series evaluated at some center. Not evaluated, but expand. Okay, expand certain center here. So I said that this power series is special, right? Why is it special? Because we look at a specific coefficient. So what sort of coefficient you get? It's just the derivative. Okay, derivative of f. So imagine you need so many derivative of f. This means what? This means that your f should be infinitely times differentiable. Otherwise, you cannot get all these derivatives. Okay, so when we discuss about this question, right, actually your function need to be infinitely many times differentiable. Okay, otherwise you cannot get all these Cn. So you can check at any point. Okay, you can center at any point. I mean, any point in the domain for your function. Okay, so how to show this? So our goal is to show this. So what's the principle when we approach series? We look at the n partial sum. Similarly, here we also look at the n partial sum, but we give them a special name here. So let's define. So we'll define the n degree Taylor polynomials. Okay, n degree Taylor polynomial of f at A is what? Is the n partial sum. Okay, it's the n partial sum of your Taylor series. So we give it a fancy name here, Taylor polynomial. Okay, n degree Taylor polynomial. Okay, so we give this n partial sum a fancy name to tell you that to tell you what? To tell you that this n partial sum is coming from the Taylor series. Okay. So if you want to show these two agree, meaning what? this partial sum here, when you take limit to infinity, the difference between fx and the limit should be 0. Okay, so let me write down here. If to achieve the goal, what do we need? We need that fx minus this limit here should be equals to what? Equals to 0. Okay. In other words, what? In other words, fx is equals to the limit of this partial sum. Okay, so we try and relate back to what we have learned at the start of series. So another convenient way to set it is what? You can, what can you do? You can play around with this equality again. Can you bring the limit up? Can you do this? Can you bring this limit out? Okay, so maybe a bit confusing. I put a big bracket here. Can you bring the limit out? Bring the limit out. Why? Conversion what? Conversion what? A sequence. Why sequence? Fx is what? So if you look at this, you can fix your x first because it is not depending on x. You fix x first, then fx is a constant. But this one, why is it a sequence? Remember, how is series related to sequence? We look at the n partial sum. So these are the n partial sum. We call it n degree Taylor polynomial. But why converge? Because our Taylor series have a radius of convergence. So we put everything together now. Okay. And then, so we look at this quantity here. This quantity has a name. Okay, this quantity has a name. So this is called the remainder of the Taylor polynomial. Or to be precise, maybe we can add, this is the n degree remainder. N degree remainder. Okay, so to denote that, this is Rnx equals to fx minus tnx. Okay, does it make sense? You know why is it remainder? Because in our mind, we want what? We want to express this fx as a t infinity. But we first take the n term, the difference between fx and the n term. So what do you left? You have n plus 1, n plus 2, n plus 3, and so on. So those things we call the remainder, leftover. Okay, we want this leftover obviously to converge to 0. Okay, so that both sides is equal. Does it make sense? Okay, so our question turns to whether this remainder here equal to 0 or not. Okay, make sense? Okay, so let's see. Right. So because in our course, we don't do this limit stuff, right? So we need extra tool to make sure this limit go to 0. So the tool we're gonna use here is called the, let's put a theorem here. So what color should I use? Let's use this one. So let's put a theorem. How about use black, red? So we need a theorem here, which is called the Taylor inequality to help us compute this limit. Okay, so Taylor's inequality. So what's this theorem here? So let's say if you have control on the n plus 1 derivative, okay, if you have a control on n plus 1 derivative here, okay, bounded by a constant m, okay, for a interval of x, okay, then you can control your remainder. Okay, how do you control your remainder? This is very handy. Comes in handy. So how do you control your remainder here? Your remainder of n is less than or equals to m over n plus 1 factorial. Okay, times the power of x minus. So you will have a bound of Rn. So I'll remind you again, what's this Rn here? So let me spell out what is this Rn here. This is just fx minus Tn. Okay, what is Tn? Recall again, what is Tn? This is the sum all the way up to Fn over n factorial times x minus a to the power n. Okay. So this means what? You want to check the remainder of the n degree, but you have the control for the next leftover term. Okay. Somewhat, if you can control the next leftover term, you can control everything that get left over. So you no need to talk about Fn plus 2, Fn plus 3, plus 5, plus 6, so on. You can control everything already. If you can control the next n plus 1 term, you can control all the leftover sum. Because R and X contain all of them. Agree? If you don't agree, let me write down one more line. So this line will be what's the leftover here? So I think it's good. 1 over n plus 1 factorial. 1 and then plus so on. Okay. So all the leftover here are somehow bound by the first guy here. Be strong, very strong at this. But I won't prove it. Yeah, maybe you can try and prove it. Do it in the project. This actually, let me warn you a bit. This topic is almost the last topic in MA. Last topic. Because you can imagine I use so many things together this now, right? So sequence, series, one, why? Yeah. It's okay. I want just that you need to prepare for the length that you need to study. Okay? I won't. Hey, when I won, I didn't say you cannot do. I'm like the Western parents. You know Western how they bring up their child. You know how they brought out their child. The very small kid, they just throw into water. You know. Does your parents dare to throw you into the water when you're a baby? Yes. Or maybe you was Western type parents. But usually Asian parents won't do that one. 不要靠近水，不要煮江边，不要动。You know? Okay. So this is a difference between Western and Eastern. They let you to experience first. I mean, if you really look at those Western child, they won't do something weird also if you let them go and try it out. You know. So I have a explanation for this kind of phenomenon. Not theorem, but at least my conclusion is, I guess sometimes Asian parents are scared about responsibility. Because you need to imagine, let's say you let the kid handle the food by him or herself. What if it drop on the floor? Who have to clean it? Would you ask the baby to clean it or not? No, right? Parents have to clean it. Maybe they don't want to clean it. So they ask the baby, don't take. Huh? You get what I mean? You get what I mean or not? Okay, yeah. So so if you realize this, then maybe you can have a different approach to your future child or maybe others.
So you need to learn to take responsibility. Okay, let's say in real life, seriously, that baby dropped. Baby. Okay, maybe let it grow a bit, drop it. First time. Okay, first time drop it. You choose to scold this baby or you choose to tell this baby. This make a large difference. Okay, so that's why I will focus on discussing. For example, those retake students come to my class. I will discuss with them. Do you really want to continue this class? Okay, if you have a heart to continue, then we continue. Okay, I won't how to say fail you. Okay, if you really put in effort. Okay, if you don't want to do it, no matter how I convince you, you also won't do it. Okay, no. So it's not by threatening, it's not by punishing. Okay, we need to have a talk, consent. Okay, if you want to work it out, you will definitely work it out. Okay, does it make sense? Okay, yeah, about responsibility, I would say. Okay, a lot of decision is depend whether that leader or that boss want to take responsibility or not. Okay. Yeah, boss. Or a previous boss. Okay, never mind. Let's continue. So right. Okay, so good thing about this is we have a theorem here. So another theorem. Wow, so many theorem before we do assignment. Right. Let's put all the theorem first, and then I'll tell you how to use all of these. Okay, finish another assignment, another theorem, and then we will do exercises. So the theorem is you really need this statement to confirm some calculation. If fx equals to the n degree of polynomial plus everything behind, and this limit of remainder goes to 0, okay, within the radius of convergence, then what? Then we will say that fx is equal to the whole Taylor's polynomial. Okay, maybe you will ask one thing here. Isn't it obvious, this statement here? Isn't it obvious? It is quite obvious, but it still requires proof. So where's the technicality here can appear? So the technicality will appear here is about this infinity thing. Okay, can you relate this limit of Rn to this equal sign here? This is a technicality here. Inside here, there's technicality. Remember, your limit is defined by what? Epsilon delta. And then this equal signs means what? You need to explain. Because in principle, you cannot add infinite things together to get a finite thing. Right? If you put into a computer, how many digits you need to put in? How to put infinitely many things inside? Cannot. The computer will jam. I don't think quantum can even do that. Quantum only speed up your calculation, but I don't think it can process infinite unless it's a god. You need a god computer. But anyway, so there's technicality to take care here. Okay, although this statement seems very, obvious. I wouldn't say easy. Obvious should be true, but there's some technicality you need to take care of. What is equal to an infinite thing? Okay, how this limit can produce this equal sign. Okay. But we don't care. Okay, in this course we don't care. We just use. So how to use? As long as you can prove the sufficient condition, you will get your necessary condition. Okay, you just use it. So how do you use it? So you need this limit condition here to hold true. Okay, before you can conclude a function is equal to the Taylor Taylor series. Okay, and then how to produce this proof here? Okay, how to produce this proof here? I gave you a Taylor inequality here. Okay, I give you a Taylor inequality here. So can you imagine how to use it or not? If you have this bound, how to show the limit of I is equal to 0? So if you put limit on Rn, that's the limit of what? Limit of what? What type? Limit of Rnx is what type of object we have learned. In this topic, we only really learn two things: sequence and series. So limit, what type of object we can put on? We define on sequence, and in calculus you learn on function of real number. In this case, Rnx, should we view it as a function or should we view it as a sequence? Depend on the limit you take on. So the limit I take is what? N to infinity. So if you take n to infinity, what kind of limit is this? It's a sequence. So you should think of this x as a fixed point. So this is a sequence limit, right? But you know that your sequence is bounded above by the other sequence. So what? So what? So what? This sequence here, what's the limit of this sequence? The limit of this sequence. What's the sequence? What's the limit of this right hand side sequence here? How many things depend on n? Two things. Okay. If this one go to infinity, this is good or why is it good? Converge to 0. How about that one? Depend. Right? Depend what is x minus a. Depend. Okay. But do we know anything about x minus a? We sure? Read the statement again. What is x minus a? We care about x minus a within a region, a fixed region. So we can actually go further a bit. This is less than or equal to m over m plus 1 factorial on d to the m plus 1. So if you can have some more information on d, maybe this limit here will converge to 0. Okay, if it doesn't converge, then you cannot say anything because you are bounded above by some divergent sequence. Okay, if the limit of this sequence here is 0, then you are good. We know that limit of Rn is 0. By what? By what rule? By what rule? If I know that the limit of this sequence is 0, then this limit should be 0. By what rule? Not quite. This is sequence. Convergence test is used in series. You should use what? Squeeze theorem. Why is it squeeze? You see, this is a modular sign here. So actually, you're bounded above by this guy and the negative of this guy. Okay, so if the two guy go to 0, then the middle guy go to 0. Okay, so we try to bring all things together, sequence, series. So in your mind, you should separate them up clearly, so that you know what tool you can use. Okay, don't confuse with a comparison test and squeeze theorem. I know it's easy to confuse, but once you ask where I can use comparison test, where I can use squeeze theorem, then it will split up already. One is for theorem, one is for series, one is for sequence. I don't think we have squeeze theorem for series, so don't confuse. Okay. Okay. Good. Okay, so let's do the EX example now. So we found the macro series, and then we try to use this method to prove that EX equals to that power series with coefficient 1 over n factorial. We prove it once before using the ODE way. Now we're going to use Taylor way. Okay, use Taylor method to prove it. So let's do it. So move this down. So
So we continue this example. We found the Maclaurin series, and then we want to show that they equal. Okay, so let's continue. So we want to show that EX is really equal to the Maclaurin series, which is what? 1 plus x squared over 2 factorial plus x cubed over 3 factorial, then so on. Okay, so actually we've shown this before, right? In the first hour, we used ODE method. Okay, now we're going to use the Taylor method to show it. So by the theorem before, what do we need to show? That a function is equal to the to its Taylor series. We simply check that the remainder, the n degree remainder, has limit going to 0. Okay, we just need to check this, the difference between f and the n degree polynomial. Right. So just now I give you a hint, right? We need to use Taylor inequality to do this. So in the Taylor inequality, what do we need? We need to bound what? We need to bound by the, we need to find bound for the n plus 1 derivative. Okay. But what is it? So if you go and compute the n plus 1 derivative of x, what do you get? You know that ex, the n derivative of ex is just ex. Okay, so this is just ex. Okay. So we don't want to look at for all x, right? So in that theorem, we just fix our x in some region, correct or not? So in that theorem, we have x minus a less than d, right? So in this case, our center is 0. Okay, so we just fix some small region around 0. Okay, so this is the condition we had in the theorem. So in this case here, right, so what do we get? We can find the bound for this e to the power x. So this guy should be bound by e to the absolute x, which is just bound by e to the d. Okay. So what does Taylor inequality tells you? Okay, so Taylor inequality tells you how you bound your Rn. But note that this Rn is greater or equal to 0 because we take the modulus. And on the other side, what's the formula given? This is less than or equals to the, so this is the m inside my theorem. Okay, so this is the constant bound over m plus 1 factorial times what? Times x minus a. So a in this case is 0 to the power n plus 1. So you are bounded by the next term. Okay, next term. Good, you are bounded by the next term. What is this? So on one side, the limit, okay, sorry. So this 0 here will converge to 0, obviously. So the hope, if you want Rn to converge to 0 is what? You need the squeeze theorem. Squeeze theorem, what do you need to satisfy? This guy go to 0. Okay, so you ask yourself whether the right sequence has limit to 0. Okay. So it turns out that what? It turns out that this is 0. Why? So first of all, e to the d is a constant. Yeah, e to the d is a constant. So you need to argue why this quotient here goes to. So why this quotient goes to 0? So in your note, right, they take it for granted that this thing is go to 0. And so assume that you know that this thing go to 0. Okay. But can you think of a way to explain why this go to 0? I mean, how do you make sure that this doesn't grow as fast as your n plus 1 factorial?
This one is also growing by power of n. How do you avoid? Yeah. The numerator grow. Yeah, how do you prove it? Okay, so there's one argument that I could give that maybe uses just what you have learned in calculus 2 is this guy here, right, appear in what? In the power series of EX. But we show that this power series converge. Converge, right? Converge everywhere. Okay, converge everywhere. So you have test of divergence. Test of divergence says what? If the series converges, limit of all the AN will go to 0. Then this is the AN for your convergent power series. I think this is the argument I'll give without going into epsilon delta sub. Agree or not? Agree? Agree? Just use test for divergence. Yeah. So let me write down. So I write here, it's true. It's true since the sum of xn over n from 0 to infinity is convergent. We check already, right, using ratio test everywhere. So by test for divergence, we know that the limit of the AN, so in this case here, limit n to infinity of xn over n is 0. Oh, first time we use the statement. Usually we use contrapositive. Sorry? Oh, sorry, n factorial, thank you. Okay. Yeah. Okay, so in the end what? By squeeze theorem, we deduce that our remainder really go to 0. Okay, by squeeze theorem, our remainder really go to 0. Then we can conclude that. We can conclude what? So we can conclude what? So we can conclude that EX equals to the sum of n equals 0 to infinity of xn over. Okay, so I have produced two ways to prove EX equals to this power series. Okay, first way using ODE, second way using this Taylor polynomials. Okay, so you can see, can you compare which method is better? Which method is better? Or even what does it mean by better? Okay, in mathematics, when we talk about better, meaning we can apply to different cases. Thus, every function will satisfy some sort of ODE or not. But you can always consider the derivative of your function. Okay, so if you can consider derivative of a function, then you can consider the Taylor series. Okay, and then you ask whether the Taylor series you get is equals to the function you started with or not. So how do you check? You compute the remainder. So you compute the remainder, and then you try to show the limit of your remainder go to 0. But how do you show it? You try to bound your remainder first by n plus 1. Okay, if you can bound it, then you can use squeeze theorem. But obviously, you can imagine you can have different way to show Rns equals 0. But we only present you this way using Taylor inequality. Okay, in real life, no matter how you show, you can get if you can get Rnx going to 0, then you can have this equality. But the method we present to you is to use squeeze theorem on R and X using Taylor's inequality. So this is just only one way. Because I think the purpose here is to let you use Taylor inequality. Okay? But in principle, as long as you can get to this line here, R and S equals 0, then straight away your Taylor series equal to the function. Sense? Still got 5 minutes. Okay. Any question? Any question about this flow or not? So, I mean, if you cannot follow, you go back and read again this flow. Okay, this flow will work for any F. Okay, if you can tell a full story about EX, then you are okay. Yeah, very good already. Because we can replace EX with anything in this story. Okay, this is the full story you need to get. Full picture you need to get about this Taylor series. Okay. So you can imagine I can change F and then you should compute the n derivative of F for other cases. And then if you compute the n derivative of different cases, then you could imagine I should bound differently. Okay, I should find a different m. Okay, to show. Let me see. Any important thing I need to go through. Okay, maybe I just go through some calculation with you and then telling you what is important. And then you can go back and try out. It's the same story. So for example, this story here, find Maclaurin series of sine x. So now you replace EX with sine x, no? And then you can go and compute all the n derivative. So if you compute the n derivative, you can check that it's cycle. You know what it means by cycling? So it has sine x, cos x, negative sine x, negative cos x, and then you repeat again. Sine x, cos x, negative sine x, cos x. So if you evaluate at 0, what happens? It cycles also. So you can think about 0, 1, 0, negative 1, 0, 1, 0, negative 1 like that. Okay, so what you left with is this series here. And this series, there's some point inside this series. Can you notice what happened here? Can you notice when the coefficient gets 0? What's left inside this series? Can you notice? If I sub all these coefficients in, can you notice or not? Who left? Who get left over? Who disappear? Only the odd power stay. What does it mean? Do you know that sine function is odd? What does it mean by odd? What's the definition of odd function? Fx equals to minus f of negative x. And all these odd functions are also, all these odd power x function is also odd function. So this expression here really captures what the original function is doing. Okay. And then you continue your story, whether you can bound the n+1 derivative or not. If you can bound it, and then see if you can use squeeze theorem or not. If you can use it, then limit of I go to 0, and then you can deduce that Taylor series is the same as the Maclaurin series is the same as the function you started with. So maybe one task you can try, your homework. Try cos x. Can you imagine what happened to cos x? Want to guess or not? What happened to cos x? Who survived? Cos x is an even function. Even function means what? Fx equals to f minus x. So only the odd power will remain inside your power series or Taylor series. Go and compute. Then you go back and compute. Okay. And then what else you need to see? Another thing to see is you can use whatever you have computed before. This is a series technique. Okay. So if you know that if you know about the power series of sine x, you can use it to find cos. Okay, one way is to do the same thing. Everything you do the same. But what do we know? We know from the previous theorem, right? Yu Liang gonna prove it. You can do term by term differentiation. Okay, if you know how to express sine x already, because we know that sine x converges, we can differentiate term by term. If you differentiate term by term, this is also how you get all the even power. Okay, clean way, very clean. Okay, yeah. But if you do this clean way here, maybe you will miss about how your derivative get come from. You can compute both way. Okay, both way you can do it, and then you can use similar method to find a different Maclaurin series based on what you know before. Okay, based on what you know before. And this series here, this binomial actually is quite computational heavy. Okay, quite computational heavy. I won't put this inside your exam, but if you want, right, you can write a full account for this calculation, in particular for your project. Okay, because if you look at the interval of convergence, it really depends on the k you have here. Okay, so this k can vary. Okay, the interval of convergence vary. Okay, but this exercise, you don't need to care too much, because this exercise is actually for the use of the next few example. But anyway, this few I think you can understand if you're going to read it. But okay, before we finish up this chapter here, I want to introduce this one. So far, where have we been? First, we introduced this geometry series, and then how to go to 2. We simply what? Can we just integrate it? Yeah, we just integrate it. Okay, and then we replace x by minus x, and then you will get this swapping. Tangent inverse is through calculation. Okay, I didn't show you, but I told you about the pi story, right? That exercises tells you how to get this tangent inverse. Ex, I proved twice to you. Okay, how to get this power series representation. Sin x, I just show you just now. Okay, you can see that all the odd power remain. Cos x you can obtain from sin x by term differentiation, and then 7 is the hardest one. Okay, so these are the basic Maclaurin series. Okay, basic Maclaurin series, and then you can use this Maclaurin series to compute other related function. If not related, then you need to compute everything again. So this kind of exercise, you see this arrow thing, you can try it out, but I think I won't care. I don't care. I care about how you talk about these Taylor series, how they equal, how you bound stuff. Okay, but this error, I wouldn't care much. If you want, you can learn. That's fine. There's no harm learning. But I won't test. This is something I want to make clear. And then all these are just finding the first few terms. So it's a subset of what we are doing. Where I found everything for you. This one just asks for first few terms. Okay, but there are some technique here. You see, there are some technique that I don't really want to say about. It's like a half done division like that. I mean, yeah, not very important. I think for the moment, but you can learn. I won't test also. Because I focus more on this theory. Why is it working? Okay, and then simple calculation. Simple calculation you have to do. For example, the EX example. You need to able to tell a full story about EX. Just now I tell you, right? There are 2 stories. You need to be able to tell the full story. Obviously, you cannot repeat now, but you need to do revision and then make sure you know how to tell this full story. For example, let's say a student council met a student lecture. You should be able to do this inside the lecture. An example, I don't know. I didn't ask you to prove Taylor inequality. I didn't ask you to prove anything. Example, you should be able to tell first. Only then we go deeper. Hey, why this step work? Why this step true? Why we need this? This one is second step. First step, you need to be able to tell story first. A workable story. And then the next step we'll say, oh, why is this workable? We dig out the detail. First, you need to at least tell a workable story first. So this is the thing that I just require you to do. So if you can do a better job, then is to explain why each step work. This is the second stage. So you need to reach first stage first. Because people tend to go to second stage without knowing first stage. Then what situation will happen, do you know? You know what happened if you jump step? Every time if you explain to the student, the student will just get confused. Why do this? 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 Why need to do this? Because they don't know the whole story yet. Once you know the whole story, you will know why we need to do it. And then I explain why this step is crucial. If I just tell you, do this, do this, do this, do this, do this, then you don't know why you are doing this. You get what I mean? That's why I was reluctant to teach step. Steps should come naturally after you know what to do. If I just teach step, you don't know why. Maybe you are a good follower, but you cannot do anything more than following. What if your leader asks you go to die? Do you go die? Because you just know how to follow. It's a very important question. More important than doing this calculation. But this is what you're going to learn, okay, if you do maths properly. This is more important than calculating this Taylor series out of one. These are nothing on. Okay, yeah, more important thing is you have to figure out your own way. Okay, figure out your own way. And then you know what to check, you will automatically line down the step by step. So whenever people, so if people give you a procedure, you should guess what's the thing that these people thinking behind. Why they ask me to do this? Okay, once you get what they are thinking, right, you can even change their procedure. They are still happy about it actually. As long as you achieve what I want to do. Because most of the time, the procedure that people give is not optimal one. Because it's just based on one view or one side of perception. Okay? If you have a better perception, then maybe you can change the system already. Yeah, so I rarely teach step by step one. Because like last time, humble one. Remember the case of humble? Should we try induction? Should we try what? Expand everything? Divide. Just by dividing, we clear everything already. Does it make sense or not? Okay. So I wouldn't claim which one is optimal because always people will come out with a better and better and better way. Okay. So I don't want to claim I'm the best, but one skill you need to remember is how to differentiate different method, different answer. You need to start to appreciate all these things. Because in different viewpoint, we'll have different understanding. Okay? No one is more, no one is less. You need to understand all. Sense? Think about it. Because later will be extremely important when we get into abstract idea. Just now it's just some function calculation, but future you'll get into abstract idea. Actually, what? Hey, counting apple is easier than counting 1, 2, 3, 1, 2, 3 is abstract, Why ask kindergarten to learn abstract stuff? You think 1, 2, 3 easy? Then why is abstract, One can represent one apple, one banana, one person, one pen, one school, one family. One is an abstract concept, Very abstract. Why 1 + 1 is 2? Dangerous, you know, very dangerous. Okay. Yeah, very abstract. Number is already very abstract. Okay, it's not about pure maths. Number already abstract. Okay, you need to think about this thing when you do maths. Okay, what time is it? Yeah, 12 o'clock. Any question? Any question? No, no. Okay, we'll see you. So extend to tomorrow night if you like. If you can submit earlier, you just submit. That's fine. See you next week.
上课